Y'all get the update on school? Pretty sure everyone's sharing it like crazy. Yeah, that doesn't sound good. So I'm trying to print out the material that I need, but for some reason this thing decides to jam. Y'all heard about school? Y'all know you're not going back this year? Yeah. Yeah. There we go. got the pages that I needed. Okay. Now that I got those printed out, I can get started. It does stink about school, unfortunately. Once again, a once-in-a-lifetime situation. But it's one of those things where you'll look back upon it, and I don't know, it'll just be one of those memories. It's really weird. Hopefully, once you watch that video I sent you about how the AP test is going to be taken, it's going to be interesting. I watched a few videos from some AP tutors talking about the desire of College Board to prevent cheating, but knowing that it'll still happen. But the way that they have the test designed and the way that they have it set up for you to submit it, it's like you don't have a lot of time to cheat. It's like the time starts, and if you're not there, you're not there, you know? And if it takes you, or if it takes someone who's helping you cheat like 20, 30 minutes to help get you the answer, then you might be out of time. You know, it's an interesting thing. But regardless. So, in the description of this video, there is the PDF link, which will take you to the file that I'm working off of today. Based on the responses that I got for the assignment, I decided that I'm going to organize them a little bit better, a little bit more focused in future videos. But mainly, it boiled down to two main things. A general hope to go over and review hypothesis testing, and a general hope to review and go over and everything linear regression, which is perfectly fine. I mean, there are other details that I'm going to go over as well in future review videos. After this, I'm going to go into the description and do a whole timestamp thing so that you don't have to go searching through the parts that you need to rewatch and whatnot. But yeah, let's take it a bit at a time. Now, in the PDF file, there are 10 multiple choice questions. I'm going to do those a little bit later. Right now, I would like to focus my attention in the PDF to number 11. And basically, my goal for this is to go through each problem, decide, well, what type of test do we hope to use? What formulas we might need for them to come in handy? And basically, how do we execute it? So let's talk about number 11. See if I can zoom in on that. I haven't tried zooming in on this thing in a while. Come on, you. Zooming in. Oh, that's better. Better than nothing. Okay. And again, if you have any questions while we're doing this, please, by all means, make sure you ask them live in the chat. And we can answer them then and there. So I'm looking at number 11. The president's job approval rating is always a hot topic. Now, you may have seen this before, but that's okay. We'll do it again. Your local paper conducts a poll of 100 randomly selected adults to determine the president's job approval rating. A CNN USA Today Gallup poll conducts a poll of 1,010 randomly selected adults. Which poll is more likely to report that the president's approval rating is below 50%, assuming that his actual approval rating is 54%? Explain. This one doesn't require a hypothesis test, but that's okay. It's still in the realm of the formulas that you'd use for proportion samples. Now, not that you actually have to conduct this, but in terms of a standard deviation, it would be something along the lines of the square root of PQ over N if you had to conduct a standard deviation. Now, a lot of the time, you don't know what the P is, the P being the population P. So you may have to conduct a standard error, which is in the same realm, except you would be using the p hat q hat over n. The point of me saying this is the n, the sample size, is always going to end up being on the bottom of that fraction. And because of that, the larger the sample size, the smaller the standard deviation, or the smaller the standard error. The larger the sample size, the smaller the standard deviation in terms of constructing, let's say, a confidence interval. So the question being, there's a local paper with a sample size of 100, and then there is a CNN poll with a sample size of 1,010. Which poll is more likely to report the president's approval rating below 50%, assuming that his actual approval rating is 54%. So they do give you that piece of information, which is that P. They do tell you that P is equal to 0.54. They're telling you to assume that, the population parameter. So it would be a standard deviation that you would potentially calculate. Oh, Kyle, you're already answering stuff in the chat, I see. Okay. Well, in terms of that standard deviation, you would have a larger standard deviation with smaller sample size. It is more likely that you would get an approval rating below 50%, as Kyle is saying, with the smaller sample size. The smaller the sample size, the larger the variation. The smaller the sample size, the larger the variation. And it's because of these formulas, because the sample size n is on the bottom of that fraction. Here's another one from that set of chapters. Let's talk about number 12. So let me flip down to number 12 real quick. Could you see any of that I was writing? Yeah, hopefully you could. I'll have to zoom out just a tiny bit more. Again, this just being a general review. Number 12 is one that I saw wrong on past assessments this year, and that's okay. We'll talk about what the heck we have to do with this particular problem. A box of Raspberry Crunch cereal contains a mean of 13 ounces with a standard deviation of 0.5 ounce. The distribution of the contents of the cereal boxes is approximately normal. What is the probability that a case of 12 cereal boxes contains a total more than 160 ounces? Now this goes down to sampling distribution models. This was the chapter we did on sampling distribution models, which was on a few of your responses that you guys gave me to that assignment. Sampling distribution models. Let's go through it a piece at a time and write down any pertinent information that we may need. A box of Raspberry Crunch cereal contains a mean of 13 and a standard deviation of 0.5. That is a broad statement. That is a population statement that they're giving you. They're basically saying, okay, assume a mean of 13 ounces, assume a standard deviation of 0.5 ounces for the population. Then they're telling you, okay, assume the distribution of all those cereal boxes of the population, assume the population is normal. Now, okay, you could construct a normal curve if you want to, but that's not necessary for this particular problem. The distribution, no, I read that. What is the probability that a case of 12 cereal boxes, now all of a sudden you're dealing with a sample of 12 cereal boxes, will contain a total more than 160 ounces? There are two ways to get this problem done. Two main ways to get this problem done. They're basically saying, okay, in a sample size of 12, if you did 160 divided by 12, what are the chances that you would get an X bar of more than 13.3 repeating ounces, which I'll put the fraction in there as 160 over 12. if you were to go about it in that fashion, if you were to go about it in terms of the 12 boxes averaging that proper number of ounces, you could do something of a normal CDF, parentheses. Sorry, I hear people screaming in the other room, and I hope that they're okay. Anyway, 160 over 12 gave you that 13.3 repeating. I'm just putting it in there so that I don't have to type in the decimal, so that I don't have to round it. So that average, comma, big number, comma, an assumed mean of 13. Now, in terms of the standard deviation, this kind of messes us up just a little bit in terms of the standard deviation, because there's several ways to calculate the standard deviation, and this is the part that I saw a lot of people did they did end up getting wrong on this thing, and I want to be very careful with how we go about doing this. I want to be very clear with how we're doing this, because you're dealing with a sample size of 12. You're talking about a standard deviation of 0.5 over the square root of 12. That would be the generalized sample mean sample standard deviation. For example, I believe we did something like where it was like the mu of x bar would be equal to mu, and the sigma of x bar would be equal to sigma over the square root of n. What chapter number was this? Now I gotta look up a chapter number this was. I want to say that this was chapter number 17 or 18. I have it right here. It's chapter 17. It's chapter 17. So, if I'm doing normal CDF, and you can type this in exactly as is, 160 divided by 12, comma, some big number, comma, 13, comma, 0.5 over the square root of 12. And it gives you a chance of approximately 0.0105, I guess, if you wanted to round that, which is perfectly acceptable. Can you see those formulas? Yeah, you kind of see those formulas at the top. Let me zoom out just a tiny bit. Come on, you. Zoom back out just a tiny bit. There we go. Good, 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 good. Good. Just want to make sure you saw those formulas at the top. Those were formulas that we got in chapter 17. Now, like I said, there is more than one way to do this particular problem. There is more than one way to do this particular problem. If you were to actually do it with 160 ounces, meaning a grand total, you're not taking an average this time. 160 ounces, comma, big number, comma, well, 13 times 12 is 156. 156. But again, how do we do the standard deviation? That becomes a point of contention, per se. How in the world do we go about doing this particular standard deviation? Well, in this particular instance, since you're dealing with 12 independent boxes, the standard deviation in this particular calculation would have to be 0.5. You'd have to convert it to variance. Then you would have to multiply it by 12. And then you would have to square root it back. These are 12 independent boxes. If you were to take 0.5 squared to turn it into variance, multiply it by the 12 boxes, and then square root it back to be a standard deviation. Well, I'm not going to write that decimal. I'm just going to put the square root of 3 here. Doing that calculation should get you the exact same answer that we got before. Normal CDF, 160, comma big number, comma 156, comma the square root of 3. And you can see it gets you the exact same decimal that you got before. Now, with these problems, again, there's a bit of decision making that has to be made at the beginning. You can choose whichever direction you're going to go. But if you're talking about an average of 12 boxes versus the sum total of 12 boxes, if you're taking the average of 12 boxes, it's almost like you're taking the average of the standard deviation. I say almost because it's not exactly. It's 0.5 divided by the square root of 12. That's the way that the standard deviation would have to be done in these sampling distribution models. Whereas if you're taking the total of 12 boxes, you would have to assume 12 independent boxes being added together, which would give you the 156 assumed mean. But then, of course, the standard deviation, you would have to convert it to variance, add 12 of itself, and then square root it back. These problems are strange, but obviously they do get you the same answer. Now, for number 13. In number 13, again, this begins the hypothesis test confidence interval discussion. Which one do we use? What do we need in order to use them? Let's go through it a piece at a time. Number 13, a random sample of 150 men found that 88 of the men exercised regularly, while a random sample of 200 women found that 130 of the women exercised regularly. Stop there. Think to yourself about what they've given you in this problem. First of all, they talk about a random sample of men and a random sample of women. It's definitely a two-sample problem. Now, being that, yes, it is a two-sample problem, it could be proportion, it could be means, but look what they're saying. Out of 150, 88 of the men exercise regularly. Out of the 200 women, 130 exercise regularly. The response to this is either going to be a yes or no. Yes, I exercise regularly. No, I don't exercise regularly. This is categorical data. And since it is categorical data, we are dealing with proportions. It's a two-sample proportion. Now, I don't even know what the problem's asking me to do. I haven't even finished reading the question yet. But let's get into that. Based on the results, construct and interpret a 95% confidence interval for the difference in the proportions of women and men who exercise regularly. Now, eventually, I am going to create some kind of formula sheet of my own for you guys to use, which obviously, considering you're taking the test at home, why not? But for this particular problem, you're talking about a 95% confidence interval for the difference in proportions. Let's see what the heck this thing has in store for us. Well, the formula, you know what? I'm just going to write it as an M and a W, just so I don't have to rewrite it. Here we go. Now, I'll talk about the standard error in a moment. For the difference, I don't know what these decimals are at the moment. I'm going to have the calculator do it for me in a moment as well, but I'm also going to do it by hand using the formula. But I don't know if the difference for men and women, I don't know if that's positive or negative. We'll find that out in a moment. But in terms of combining the standard errors, the standard errors for men, let's just say, would be p hat q hat over n square root the whole thing. For the women, it would be, for their numbers, p hat q hat divided by n square root. In order to combine them, once again, you have to square to variance, add them together. You add them no matter what. That's not a typo. Then square root them back. So, whatever the proportion for men is, the p hat for men, q hat for men over n, if you were to square it to variance, the square root would go away. Plus the p hat for women, q hat for women over n. Again, square it, the square root goes away. Add them together, square root back. That would give you the combined standard error. When it comes to these proportions, if we were doing, let's say, a test, if we were doing a two-proportion z-test for this particular problem, we would get a slightly different standard error, which I guess we'll find out what happens. We don't actually have to do the test for this, because they're still saying, does your confidence interval support the conclusion, which we'll get to in a minute. But if you were to be doing a test, you would have an assumed difference. The assumed difference would be 0. Thus, we would have to do a pooled standard error. But that's not for this problem. For this problem, you don't know what the population parameter is. You don't know what the population difference is. So we have to assume to be different. So let's just see what happens. I'm going to, let's see, what is 88 divided by 150? That's terrible. And 130 divided by 200? 0.65. Okay, so apparently the proportion of women is greater than that of men. That's okay. I'm going to do it the way that I have it written on this paper, just for fun. Let me do it like this, actually. Let me do 88 divided by 150, and let me store that to m. And let me do 130 divided by 200, and let me store that to w, just to make it easier for myself a little bit later on. I'm going to use m as that decimal, and w as that decimal. So let's see what happens. First, I need to calculate a standard error here. So this would be a giant square root, men, parentheses 1 minus men, divided by the sample size, which is 150, plus w, parentheses 1 minus w, parentheses divided by 200. There's my standard error. Let me store that to s, but there's my standard error. Let's just see the difference between them. I'll write down the difference in a little bit, but I need to get a z-star. You're doing a 95% confidence interval. Hopefully you can see that. Yeah, you can see that a little bit. If I'm going to be doing 95%, that means that I got to be doing 0.975 for the 97th and a half percentile. So I'm going to be doing inverse norm, 0.975, 1.96. Let's see. This would be approximately 1.96 times 0.0525 rounded. Let's see, what was m minus w? Negative 0.063. Again, this is if I was doing it by hand. I can show you what the calculator will do in a moment. B plus that. Let's do the inverse norm. Inverse norm 0.975, get the exact number, times my standard error. And then that minus my inverse norm 0.975, parentheses, my standard error. There we go. Oh, there's a glare. Again, this is doing it by hand. Of course, if you had a calculator, your life would be 1,000 times easier. Your life would be 1,000,000 times easier. Of course, if you're going to be using the Matt Bogner website, he should get you a very similar answer in terms of a confidence interval. If you have a graphing calculator on your hands, though. If you have a TI-83, a TI-84, whatever the heck that you have. Life is so nice when you can just go straight down to 2prop zint and type in the appropriate information. 88 to 150, 130 to 200, 95% confidence. And you can see the exact confidence interval that the calculator got was the one that I wrote down. And again, this is the difference of men minus women. If you do it in this order, you have to type them in that order in the calculator. Now, if you had to interpret, this is based on the results, construct and interpret. If you are interpreting, you are going to have to make a statement. We can say that we are 95% confident the true difference in proportion of men and women is in this interval. We are 95% confident that the true difference in proportion is in this interval. Negative 16% to positive 4%. And again, that's men minus women. If you did women minus men, it would be a slightly different interval. It would look different. You have to be careful. But let's work with this one. Part B. A friend says that she believes that a higher proportion of women than men exercise regularly. Well, we have some evidence to that effect, being that the proportion of women was larger than that of men, but does your confidence interval support this conclusion? No. No, it does not. And the reason that it does not is because 0 is in this interval. Yes, there are some numbers that are negative, some numbers that are positive. But 0 is the make or break number. Because 0 is in your confidence interval, that is evidence to suggest that there is no difference between men and women in terms of the percent that exercise regularly. Because 0 was in that interval. Now, if you're saying, again, men minus women, if you're saying that women are more, then you'd be like, oh, well, then it should all be in the negative range, which a large number was in the negative range. However, because 0 is in that interval, that not nullifies it, but it's not evidence supporting your friend. It's evidence against your friend. Let's look at number 14. Confidence interval. Which one do we use? I see percentages already. And because I see percentages already, then I'm going to be dealing with some kind of a z interval. Again, if you're dealing with anything with proportions and categorical data, you're going to be using the normal distribution for the most part. A recent Gallup poll found that 28% of U.S. teens aged 13 to 17 have a computer with internet access in their rooms. The poll was based on a random sample of 1,028 teens and reported a margin of error of plus or minus 3%. What level of confidence did Gallup use for this poll? Let's see. Recent poll found that 28% have a computer with internet access in their room. Okay. The poll was based on a random sample of 1,028 and reported a margin of error of plus or minus 3%, which I'm going to write down as 0.03. What level of confidence did Gallup use for this poll? Now, again, if you're looking at that formula, there's the formula that you need. You could, if you wanted to, just start throwing numbers in. However, because they're only asking for the level of confidence, we need to first get Z star. And since we're looking to get Z star, your margin of error is everything after the plus or minus. You would simply be putting 0.03 equal to Z star times the square root of 0.28 times 0.72 over 1,028. This is the setup to this problem. 0.28 times 0.72 divided by 1,028. Again, with confidence intervals, you don't know what the population parameter is. That's why they're using p-hats and q-hats and whatnot. But this is what we have to solve. Now, when I do this next calculation, it's not going to automatically give me the answer that I'm looking for. It will give me the Z star that they used for this particular problem. Now, because you're dealing with Z, you're dealing with the normal distribution. They want to know with what percent confidence. Well, they got a Z star of 2.14, or I should say plus or minus 2.14, because that is the range on the normal distribution. There we go, that they used. Basically, if I do normal CDF, the negative of that answer to the positive of that answer, it gives me the exact percent confidence that they had. This is approximately, which I could break this down in terms of my work, normal CDF negative 2.14 to 2.14. This gives me approximately 0.968, 96.8% confident. You could always go back and check your work, of course. But this is what they would potentially expect to see. When I say check your work, I mean you could do a one prop Zient with 1,028 teams and keep guessing the confidence level until you got it right, which this one you'd have to round, unfortunately. Yeah. Which, if you actually did find the range of that, you'd find a margin of error of approximately 3%. There it is. But again, that way is going to be a bit longer if you don't know what percentage to work with, and if you're checking yourself over and over and over again. It's much, much easier to go through this process knowing the formula. Then comes number 15. Do more than 50% of U.S. adults feel they get enough sleep? According to a Gallup December 04 lifestyle poll, 55% of U.S. adults said that they get enough sleep. The poll was based on a random sample of 1,003 adults. Okay. Hold on, I'm just checking one thing. Okay, good. Test an appropriate hypothesis and state your conclusion in the context of the problem. Okay. The question is, do more than 50% of U.S. adults feel they get enough sleep? According to the poll, again, this is a poll, 55% of U.S. adults said they get enough sleep. Now, I'm going to write this off to the side. Okay. From a sample size of 1,003, this is before I actually go through the nuts and bolts of the hypothesis test. Okay. In terms of a null and alternate hypothesis, the question is, do more than 50% get enough sleep? Well, for the null hypothesis, it's typically going to be something that is equal to. Let's just assume that for the null hypothesis, as always, there should be nothing going on. There's nothing happening. There's nothing out of the ordinary. So we're going to let p equal 0.50. And the question is, do more than 50% feel they get enough sleep based on, let's say, this piece of evidence? We'll let p be greater than 0.50. The whole idea of a hypothesis test is putting a certain number on trial. If I say I fail to reject the null, I'm saying, well, I don't have enough evidence to show that more than 50% get enough sleep. But if I end up rejecting the null in this particular instance, if I end up rejecting the null, then I have evidence to show that more than 50% get enough sleep. And here's my evidence. But now I'm going to have to run through this. If I'm going to use a z-test, in this case a one proportion z-test, because I have a proportion here, I need to do a few assumptions conditions. Then, now I'm just going to verbalize this because I don't have enough room to write it all out right now, but I'm just going to verbalize this real quick. Definitely a large enough sample. If I were to check expected successes and failures, it would hit it on both ends, more than 10. I said the sample size is large enough. It's a random sample. Because it's a random sample and because we're talking about the number of hours of sleep, it is reasonable or feasible to say that the amount of sleep that one adult gets is independent of the next. Because of all this, I can use a one proportion z-test. And if I'm going to use that one proportion z-test, I'll show you two ways to do this calculation. one proportion z-test. I can type in the appropriate information. Now, if you notice for the x, I'm doing 55% of the sample size because that was the sample. It's a decimal. I'm going to have to fix that in a moment. I'm going to have to do greater than for the alternate hypothesis. You could go up to 552. Yeah, you might go. Yeah, you could go down to 551. I don't think it really matters as long as you identify what you did. So, if I'm going to identify what I did, one prop z-test, I could do p sub 0 is equal to 0.5, x is equal to 552, n is equal to 1003. The alternate hypothesis is greater than p sub 0. If I were to calculate this, fix that, there we go. I would get a p-value of approximately 7.14 times 10 to the negative fourth power, which is really a, 1, 2, 3, 4. There we go. That's what the p-value actually is. Can't see it. There we go. The bottom right there. Now, because of this, my conclusion should be to reject the null hypothesis, and it will be, and it is, because I based that on an alpha level of 0.05. And I'm going to put that into my conclusion. If you were going to do this by hand, however, you would get a more accurate answer, only because for this x, we had to round when we did the test in the calculator. If we did the decimal, the calculator would have given us an error. But if I'm looking at getting a sample result of 0.55 or greater, assuming a mean of 50%, and because I'm assuming that mean of 50%, that would have to be my assumed standard deviation. Normal CDF 0.55 comma big number comma 0.5 comma square root 0.5 times 0.5 divided by 1003. Now, obviously, again, the answer is not exactly what we got with the calculator because this one is actually more accurate. This one gives you a p-value of, well, I'll write down like that, 7.7 times 10 to the negative fourth power. There is an alternate way to get this done, and it utilizes your binomial formulas. Binomial meaning, for this particular poll, it's either yes, I get enough sleep, or no, I don't get enough sleep. There's only two results. This is a binomial, and it's finite because there's 1,003 adults. You could do a binomial. Now, again, using normal CDF, we can do the decimal number here. I'm looking at the possibility of getting 551.65, 551.65 or greater, assuming 501.5 is my expected average. That is n times p. I'll write that formula down here. Times, or not times, I'm sorry, but with a standard deviation of npq. My binomial standard deviation is square root of npq. Square root of 1,003 times 0.5 times 0.5 gives me an assumed standard deviation of this decimal, which I'm not going to type that decimal. I'll do the exact one in a moment. But this should give me the exact same result, 7.7 times 10 to the negative 4. Let's see what happens. Normal CDF, 551.65, comma, big number, comma, what did I say, 501.5, comma, that standard deviation that we just calculated, 7.7 times 10 to the negative fourth power. It gives the exact answer. There's a number of different ways to go about this problem. A number of different ways. The whole general idea of AP Stat is just finding the way that works and to go with that. My conclusion Because p-value is approximately 0, less than 0.05 alpha, I reject the null. There is evidence to suggest U.S. adults get more, I'm messing up this conclusion. I'm totally botching this conclusion. There's evidence to suggest that, I should say, more than 50%. More than 50%, there we go, of U.S. adults get enough sleep. That's what it should be. I'm going to repeat that. Get enough sleep. There we go. Because the p-value is approximately 0, which is less than 0.05 alpha, I reject the null. There is evidence to suggest more than 50% of U.S. adults get enough sleep. That would be answering the question. As a total side note, I completely forgot the 10% condition in assumptions conditions. This is why I probably should write them down, but I knew I was going to run out of room. 10% meaning less than 10% of the U.S. adult population. Love that kind of stuff. It was nuts. Now, this is just a review number one. This is just a review number one. I'm going to be going over more problems with you as the time grows closer to your AP test. Your AP test is in less than 3 weeks. I have gotten your responses via Google Classroom in terms of the topics that I would like, or I'm sorry, that you would like to cover. I'm going to organize them, I'm going to set them up together, and I'm going to put together some material, and these reviews are going to be themed. This was just a general kind of like hypothesis test inference for proportions thing that I wanted to go over with you. But yeah, we'll hopefully see you in the next one.